The BSides DC 2017 videos are brought to you by Threat Quotient, introducing the industry's first threat intelligence platform designed to enable threat operations and management, and Data Tribe, a new kind of startup studio co-building the next generation of commercial cybersecurity, analytics, and big data product companies.
Hello everyone, my name is Ariel Volivansky. I'm a security researcher at Twistlock. We do security for containers. As a part of my research, I started to look into Alpine Linux. Oops. So, how many of you do know Alpine Linux? All right, that's a few hands. So, Alpine, in essence, is a very small distro that's used mostly in containers, but for embedded things too. The motto is being like small, secure, and very simple. So, like they actually live up to that. The image itself is about 5 megabytes in size. They put a lot of effort into security. They patch the kernel with GR security and packs. That's a bit less relevant with containers, but it's good to have that. All user space binaries are compiled with Pi, no execute, full Relo, stack smashing. That's like a stack canary, and all these kind of things. These are all the features you could compile. You could put on compilation time to protect your binaries. So that's pretty useful. All right. So why is Alpine relevant? It's become very popular for containers. On the official hub, you can say like it has more than 10 million pools. You have tons of images based on Alpine. So that one is from Hacker News. The Docker company is hiring Nenel Kopa, the developer of Alpine, to migrate all images, all official images, to Alpine from Ubuntu or Debian. So essentially, you got like everyone is going to be using Alpine sooner or later because it's so small and secure and it's very efficient. So that's going to be an attack vector for people to look into. So I was looking into it to try and find vulnerabilities inside it. Right. So to do that, I would have to take an image and see what it consists of. So the most basic thing is libc. You probably know GNU libc. That's like the regular C library that you use when you just do normal GCC, but Master is just a different implementation of that. You have BusyBox, which is like, it's a package that has all the basic Linux tool that you know, like grep or ls or all the basic things. They just put it in one package, and it's very small. That's their thing. So Alpine knew that. And then you have APK tools. That's the package manager. It's just like apt-get you have on Ubuntu or Debian. You'd use it to get other packages from the official repository of Alpine. So I wanted to see what do people do with Alpine, right? When you use containers, you're gonna like take Alpine as your base, and then you're gonna do something upon it. So one of the first things is get more programs. You'd do from Alpine, and then on the next line, you'd run apk get to download something. Okay. So that's why I wanted to look into APK. Now, APK was originally written as shell script, and about 2008, they rewriting everything to C. So that was good for me as a researcher because C code means more bugs, more memory bugs, all kinds of things that I might be able to exploit in the future. So to use APK, you'd go APK update and APK add for the package you want to do, just the same as you do with any package manager. And like my thoughts were, can I somehow like damage the packages that it downloads? Can I put my code on the packages that it downloads? Can I maybe downgrade packages and use some old vulnerabilities? That would be like an attack vector. If I could make it somehow download bad packages or old packages, then the Alpine would be vulnerable. So to start, I went to the wiki. They have a pretty nice wiki with lots of details on how they build an image. So APK looks at EDC APK repository for all the list of the repositories. You can have local ones, you can have remote ones. And when you start a Docker image, by default, it uses HTTP. Okay, so that was the first bad sign, because if it uses HTTP, a man-in-the-middle attacker could just interfere with whatever they pass there and put something else. Now, it doesn't mean it's vulnerable, because they can still sign whatever they pass on HTTP. It just means someone could interfere with it. And indeed, they do sign all packages. You have EDC APK keys, which has all the RSA keys of the developers. So it's not as simple as just changing the packages over HTTP, but we might still have an attack vector here. So I looked into APK update. When you run APK update, what happens? So from the wiki again, it downloads a file called apkindex.tar.gz. Now, from that file, it takes all the list of the repositories or the packages it wants, and it just parses that and takes all the data out. So I wanted to see what that file is made of. And again, the wiki was pretty helpful. Well, in hindsight, that's a bad screenshot, but it just essentially, to make an APK index file, what they do is concatenate two files, two tar.gz files. The first one is a signature, and the second one is the raw text data with all the list of the packages. So that wiki was pretty useful, because otherwise I would just go and run file on this and try and see what it's made of, and I would untar it, and this just gave me, all right, it's two concatenated files. Now, having that signature as a tar.gz meant that the package manager would have to take that file and untar it. It would have to unzip it and untar it, and then read the signature, right? So that's a whole bunch of codes that's going to run before they even look at the signature. And since it's passed on HTTP, I could just put whatever data I want on that piece of code. All right? So that was for my next step, which was fuzzing. How many of you heard of fuzzing for security purposes? OK. So I'll just go it pretty shortly. Fuzzing means giving a lot of data to some code to make it crash. All right? Let's say you have some piece of code that parses JPEG images. You just feed it with tons of binary data until it crashes. Okay? And you check which data made it crash. Now, you have dump fuzzing, which means trying all random bytes until it crashes, just modifying the bytes all the time until it crashes. And then you have real fuzzing is instrumented fuzzing. So you have some program that takes your code, your C code or whatever, and when on compilation time, when it translates that to assembly, it puts all its own code to look at which branches you take. So in essence, when it feeds the data to the binary you run, it knows which branches it takes every time, on every execution. Okay, so let's say in the example of a JPEG, you have some magic on the header, right? So you'd feed it all kinds of random bytes, and it would just stop because the header is bad. And then once it gets the magic, it knows it takes a different branch, and then it thinks oh, I can just use that magic and get to that branch every time. And if you do that in dump fuzzing, you would just have hit that magic once, and that's it, and you'd never use that again. And in smart fuzzing, you'd keep using that magic because it takes a different branch. So what that means, you can get a lot of code coverage with smart fuzzing, and you can find crashes pretty quick. Now, AFL, American Fuzzy Lop, is a very popular fuzzer that's open sourced. It's found lots of bugs in open source projects. You should look that up. And I've used that before, and I've used that again for APK to see if it can find crashes in the code that parted the APK index file. So I went and got the source code, and I had one more step to do before fuzzing, because I couldn't just take APK and give that to AFL and tell it, all right, fuzz that. Because APK has lots of features. One of them is downloading packages and updating, but it can do all kinds of stuff. So I just had to find a piece of code that would download the packages and feed that, like feed the data from FL to that. So I found update.c. It sounded like that was going to be the relevant file, but it had nothing inside it. The main was in apk.c. That was another file. And although in the update.c, at the end, it had this piece of code that said, all right, that's an update applet. They had their own definition of applet. And inside it, I found that they did that apk update cache flag. Okay? So I just grabbed that in all the source files. And I found it in a file called database.c, which has a function that's called from the main function. And what it does, in essence, is just update the cache, update the repository cache, like go to the remote repository, download the APK index, and parse it, and do everything that I'm looking for. So I like the concept of an applet, and I wrote my own applet for APK, just so I can fuzz it easily. So I made this fd main function, and this was the function that's going to get all the data from the fuzzer. And I used their own internal function to get data from a file, which was apk bitstream from file, and I fed that to apk db index read, compiled it, and I put AFL inside a container just so I can run it quickly, and whenever I change the setup, I can just rerun it easily. And after a while, the fuzzer did nothing. AFL actually tells you that I'm not finding anything; it's all stuck. And it did have that line that said that it's not making progress. So it was stuck, and I tried fuzzing some other functions. And I kept looking into the code and find the exact function that's relevant for me, because it does a lot of stuff before reaching the top parsing. So I found apk top parse, which was the function that parses doubles. But the fuzzing was still very slow. APK gives you the speed that it takes for every execution. And it was like a few tens of seconds, which is way too much for a fuzzer. You want it to be milliseconds to actually make real results with it. So I had to find what's the bottleneck, what's making it very slow, and kill that. So I found it does init open SSL, and it does apk db init and apk db open. Well, the most important thing is init open SSL, because on every execution, it starts with init open SSL. And this function relies on entropy. And that means the Linux kernel would have to generate randomness every execution. And at one point, it would run out of randomness. And it would take a few seconds to generate enough randomness to feed init open SSL. So since I didn't need the signature parts, I just commented that out. And I went without that. And the execution was pretty quick after that. In milliseconds, it went and parsed every top file. All right, so I went and fuzzed again. And I got crashes. I finally got crashes that I can deal with. Now, when AFL gives you crashes, it's just a bunch of files in a directory that code a crash in the binary. And you can get hundreds. You can get a lot of files to look at. And what I first did was manually go for each file with GDB and try and see why is it crashing. But that was inefficient because I had, again, lots of files. So I used Crashwork. It's a nice tool. It's also open source. What it does is do exactly what I did, just automatically. It runs every crash with GDB, and it checks all the memory to see why did it crash, and it even goes as far as telling you if it's exploitable or not, and what's a vulnerability if it is. In this one, it says there's a memory access violation thing, which is nice because I could now know exactly which crashes were relevant to which bug. So I had 6 crashes that seemed to be from different sources. Eventually, I found 2 lines that these crashes originated from. But before I could have done anything with it, I had to to reproduce it with the original code, right? Because I changed the code. I put out a lot of functions. I commented out a lot of stuff. So I wanted to see that the crashes were not originating from the fact that I've changed the code and removed functions. So I took the bad crash file. I gzipped it and put it inside an apk.gz file. On my Nginx server, I used the add host flag for Docker to, what it does is change the host file on the Docker when it sets it up. So anytime the container would try and reach cdn alpinelinux.org, it would go to my server. So that's a very simple man-in-the-middle attack. And I ran apk update. And as you can see, I got a seg fault. A seg fault means crash, means I might have a vulnerability here. So this time I opened GDB with the original source, and I found the origin of the crash. And I would like to explain what was the line causing that crash. So inside archive.c, we have the apk tar-parse function. That's its signature. That's the one I used. Now, to actually make sense with why it's crashing, I had to understand how do I go and parse the tar file. Yeah, because I'm reading the source of parsing the tar file, and I have to understand what a tar is before I can actually do anything with it. So a tar is a very old format. I think it goes for tape archive. Yeah, it's very historical. And it goes in blocks of 512 bytes. Right. The first block is the header file, the header block, and then you get like data blocks, and then a header again, and then data. So the first one would be like telling you, right, the next block is the file, and that's its name, and that's its length, and then you get the data. So one of the fields of that header was a type flag. Type flag would tell you what the type of the next file is. One example is a normal file, a regular file, and another one is a link. And then you have all kind of special flags. One of them is the long name extension. Now, why do you need that? Yeah, that's an extension to tar, and they made that because you can only have files with names of only 100 bytes. Because in the header, the part that has the file name is only 100 bytes. So if you have anything bigger than that, you're going to need to tell it, all right, the next block is going to have the size of the file name. Yeah, so that what this extension was for. And I learned that because of the bug. I had no idea. Like, I didn't look into it. So that's from the APK source. What it does is check for the type flag. If it's L, then that's a GNU long name extension. And it does something pretty simple. It takes the long name buffer and it allocates it with entry.size bytes. Okay, so that like entry.size is taken from the header, and it's just the size that's going to be of the file name. That looks all right. I would implement it like that too. And then I noticed they used blob realloc. They don't use realloc and use something internal that they've written for themselves. So I looked into it, and then you'd see in blob realloc, it takes apk blob t and the new size, and then it just calls realloc on that buffer with the new size. But they did add this check. They do if b at len, which was the old size of that buffer, is bigger or equal to the new size, then do nothing. Well, why would they do that? What they probably wanted to achieve is that if you have if you want a smaller buffer than what you already have there, like I think shrinking it, just don't shrink it. Okay, they just if you need more byte, then they'd expand it. They'd call realloc, and if you're going to use less byte than what's already in that buffer, then it's okay, right? It can be bigger, and you just use part of it. So that was probably the idea behind this. But they did have some flaw in here, which was that. Well, new size is int, and b at len is long. They're both signed. Now that makes that comparison signed. So let's say if new size is anything bigger than 8,000 bytes hex, then it would be negative, right? Because the most significant byte means the sign, and anything bigger than max signed int is going to be a negative integer. So, like, it could be -1. New size could be -1, and then it would be smaller than b at len if it was anything like less than that. So, in that case, I could just, okay, so that would be okay as long as is@read would treat entry.size as signed too, okay? Because if it was like -1, then like is@read would say, all right, that's -1, so I'm not copying anything because it's negative and it makes no sense. But what happened is is@read went to gzi_read, which were the function that treated size as size t, which is unsigned. So if it would be a negative size, it would just treat it as a huge size, okay? So like -1 would be just a very huge number. And that's the origin of the crash that I had. Now, you'd think to fix that, you could just put size t in blob verilog, and then that would just, be unsigned and it would be okay. But then you have the +1, so you should like make sure it doesn't overflow the max size that you can get. And the second vulnerability I had was there's just like the same thing that I had here, just with a different type flag, which was a PUX header. It doesn't really matter so much. So yeah, so I was just going to develop an exploit for that. I was going to try and reproduce everything myself. So I started and built a small TOR file. That's the one I used on my hex editor. And I had that, you can see a small L over there. I don't know if you can tell that from here, but there's a small L, which is for the GNU long name extension. And the size is, the size for a TOR file is like in octal in ASCII, okay? So that shows how historical that format is. So I just went with 7777, which is essentially -1 if you look at it as a signed integer. And I took that file and I packed it again, just as I did before the crash, and I got a crash on the execution. Now, what happened here is that I went and started with the long name vulnerability straight away without having that buffer allocated before. So it starts with null. Well, if you don't allocate anything to it, it's going to be 0 at first. So entry at name was 0, and it just tried to copy, all that -1 bytes into 0, and it crashed because it can't copy to null. So that was all right. I just had to do the same as I did here, but put one block before that would allocate a normal size. I don't know, just a few hundred bytes, just to have that long name not 0. So I did that. I had one block that would allocate the long name buffer, and the second one would just crash it. And I managed to actually make it crash, and I used GDB, and I saw that it's overflowing. The is@read was copying all the bytes from the -1 whatever to the long name buffer, and I had an overflow. Again, so one thing that really helped me here was that gzip_read, which was the function that was called from is@read, it would stop once its source runs out, right? So if I give it -1 bytes to read, it wouldn't expect to read that amount of bytes from the file. So I could just put whatever bytes I want in the file, and it would stop when the file ends, and not when it wouldn't keep reading from the file non-existent bytes. So that was pretty helpful for developing an exploit. And I had to do something with that heap overflow. Now, I don't know how many of you have exploited heap overflows before, but there's traditional ways you can exploit an heap overflow with libc, with normal libc. Like old malloc had some unlink vulnerability. There were lots of problems with the way libc allocated the memory itself. You could just like override structs of libc. But I didn't have GNU libc here. I had musl, and I didn't want to look into musl and try to understand how I would lay out the memory. So I just decided I'd go with something simpler. I just look into the heap and see if there's anything I can overwrite over there and make sense with it. For instance, I thought I really wanted that to happen, but it did not. To have a flag on the heap that would tell it to ignore the signature. Right? I thought maybe they have a flag that says use signature, and I would put 0 on there, and they would not use the signature, and I could put whatever code I want in the packages, but I didn't have it. And the second idea I had was to go with callbacks. I thought they might have some callbacks on the heap that I can just callbacks as in function addresses that I could put any addresses I want on there and have them called. I had that idea because I know they use IS at read, which means if IS is going to be on the heap, then it's going to have all the callbacks on the heap too, and I might be able to override them. Now, that solution will work as long as we don't have ASLR, which is address space layer randomization. It's one defense method that means on every execution you have of an L file, all the addresses space is going to be randomized. Okay, so you can't know beforehand which section is going to be at which address. So if I want to call an address I want instead of one of their callbacks, I'd have to know its address. And with SLR, that's not going to be possible. But there are ways to bypass SLR today. I think most people do use, they find other memory leaks, and then they know the address space, and then they calculate everything on the spot. But I just wanted a small exploit, a small proof of concept, so I just disabled the SLR for this. Looked into the heap, and I found IS at read on the heap, as I thought. And its definition was just like that. It has 3 functions. One is get meta, there's read, and there's close. Now, I don't know what get meta is for, but it was never called, so I didn't look into it. And read was the one that actually made the copy. And I put a breakpoint on it to see its address. And I found its address. And luckily, it was ahead the buffer that I'm overflowing. Right? So you can see the difference between the long name, the entry.name buffer, to the IS struct is something like it's 0x1538 0 bytes. So on the heap, I'd have the one I'm overflowing, then all kinds of data that I don't know what's made of, and after that, the IS buffer. So I opened my tar file, the original one that I did the override in, and I put this amount of bytes with zeros or whatever random bytes, and after that I put just zeros. Now, that was pretty risky because if there was anything useful on that 15380 bytes that I overridden, I would crash it, but it just worked, and it crashed on 0, and the crash was originating from that call to IS at read. So it would just essentially call the 0 address that I put instead of that IS at read. So that meant that I can put whatever address I want on that callback, and it would be called with my parameters. But parameters. How would I pass parameters to the function that I'm calling? Right? It's going to bring whatever IS at read was getting to my call. So the first parameter it gets is IS itself. Now let's look at IS again. It starts with get meta. So that's 8 bytes of data that I could put whatever I want in, and it would be the first parameters. And I use that. So the function that I wanted to call was system. System is a syscall that takes a string, a shell string, and just executes it. So that's pretty simple for proof of concept. Let's say I just write echo 1 in it, and it would just echo 1 on it would run that. So I put echo 1 instead of the 8 bytes of the get meta, and I just ran that, and I put system in the read address, and I got it running. I got 1 printed to the screen, and then a segfault. Now, I thought that was good until I tried reproducing it on a different kernel version, and it didn't work. Now, trying to figure out what happened there, and it would just, like, since IS@read would copy in chunks, it would just copy at one time, it just copied 4 bytes instead of 8, and then call IS@read again. But the new address of IS@read would be 4 bytes of the original address and 4 bytes of my overridden address. And it would crash. So I had to find something else on the heap I could do. And I just looked in the heap again. I put all kind of random bytes in there. I put tons of A's in there. And I found GIS at BS, which was an internal pointer for the gunzip function. It worked just the same as the IS one, only it had the flags parameter 2 and the struct. So instead of 8 bytes to overflow, I now had 16 ones I could use for my payload string, right? Because I don't really care about the flags that it gets. So that's a screenshot from my hex editor making that exploit. I put echo twistlock inside the first 16 bytes. The first 8 you can see is going to be the flags. The second is going to be the the get meta function. And after that, it's going to be the read function, which I put the system address that I checked for instead. And everything after that is irrelevant because I didn't care about recovering the execution. I just wanted my code to run, my payload to do its work. So I ran it, and I got twistlock printed, and then a segfault, and that essentially meant that I could run whatever 16 bytes of shell string that I want on that Alpine. And I just, right, so I went and run a different exploit. Instead of putting the echo twistlock thing, which is pretty useless in itself, I just put like netcat on there, which listens from a port, and then I popped up a shell from a different system, and I had it working, and I just could run whatever like I want from the shell, and then when I close it, it would crash. But a sophisticated attacker could just take that and actually recover the execution, and that meant that if you do a man in the middle, the image is pretty blurred, but what it showed is that a man in the middle attacker could just take, just when you run APK update, it could put his own payload, just like I did there, and recover the execution, so you'd never know that happened. And you'd think everything is OK when you run update, and it'd get his payload running there. And that would happen anytime you'd build a Docker image based on Alpine, or you'd update your current Alpine Linuxes, and that's pretty nasty. So I promised to talk a bit about what do you do when you get that kind of vulnerability, right? I've found this, I've exploited this. That's like effective now. It could affect people right now. So how do you go about sharing that with people, closing it? What do you do? So in general, you have 3 ways to disclose, like 3 ways of disclosure for the vulnerability. The first one is non-disclosure, which means you found something and you're keeping it for yourself. You're not sharing it with anyone, or worst case, you're selling it to people. You might be using it maliciously. That's like the black hat side of disclosure. Now, on the other end, you have full disclosure, which means taking everything you found and just putting it out there, right? Just like sharing everything, including your proof of concept online, and having people use that. And I know some researchers will think that once they do full disclosure, it puts a lot of effort on the vendors to fix their bugs. And well, that's true. It does put a lot of effort on them, but it also creates a lot of chaos, okay? So what you should do is follow responsible disclosure or coordinated disclosure, which is the process of contacting the vendor privately, letting them know of the problem, and asking them to fix it. Now, there's no exact definition of how you do that, but like what I like to think is that first you'd estimate the impact, you'd write a proof of concept if you have enough time for that, and then you'd send it to them. Because some researchers just send the crash report to the vendor and they'd think they'd fix it. But just sending a crash report is not enough at all. You'd have to explain what the bug is and try and get them to fix it, actually. So just write a short paragraph, explain what happened there, and give them a few days to look at it and fix it. Now, you'd expect a response back, certainly. Now, I think most vendors do have like emails especially meant for that, right? You have a security team that are meant just for closing such vulnerabilities. So you'd expect to get contacted in a few days and know when a fix is gonna be. Like you'd ask for an estimate, and that's it. It will be closed. And at the same time, you'd want to assign a CVE ID. Now, a CVE is how many people, if you do know CVE? Right. So that's most of you. It's essentially a number that's assigned for each vulnerability. So you can look it up online and use that number whenever you talk about the vulnerability, and that way everybody knows, everybody can refer to that specific bug at the same time. So to get a CVE, you'd have to contact MITMing. That's an organization. It's a non-profit American organization that's one of the things they do is assign CVEs and organize the whole CVE thing. And they first ask you to search for a vendor that's responsible for that product that you found the bug in. So let's say you found a vulnerability in iOS, you'd contact Apple, right? And Apple would give you the CVE. But as long as it's an open source project and there's no one specific responsible for that, then MITMing is going to give you the CVE ID. And once it's fixed, once it's all done, you'd go and you'd write about it online, you'd make blog posts about it, you make an advisory. There's always safe security for open source projects. And then you'd get people knowing about the vulnerability and fixing it and issuing updates, and then the whole process of patching bugs will go for. And what I did was go on IRC, because hackers like IRC, and the developers were on IRC, so I just went there and I told them I found the bug in Alpine, what do I do? And I got to talk to Timo Teras, which was the person responsible for APK in itself. And it took him just a day or a few to fix that, and he asked me a lot of questions on how I found it and how I exploited it. And instead of just fixing this specific bug, I actually went and removed all callbacks from the heap, so my specific exploit wouldn't work again. That was nice. Most developers just closed the bug, but they went all the way through and closed the exploit too. And I went and wrote an advisory, like I said, and I made blog posts about it. And that was pretty much the end of this specific research, but it's not really the end, because there's so much still left to do. Well, I fuzzed only the top parsing function, but there's so many functions and like data parsing parts of APK that I might fuzz, and you might as well try and fuzz Alpine and Alpine stores if you have that. And Alpine APK relies on libfetch, which is a BSD library for networking and like HTTP and HTTPS, and I don't think it's maintained. I'm not sure, so I might as well check that out and try and find that, because network protocols sounds like good vector for vulnerabilities. And I'll go for a demonstration now. Demo usually don't work at current, so I just prepared something beforehand, and I'll just open it. Right, so that's me on the first the machine that I made, and the second one is a vulnerable machine, right? So here I go, and I just put my payload inside the engine server. I gzip it, just like I did before. Right. And then I check there's a connection. Yeah. Right, so what I do here is run a Docker that is man in the middle, okay? Because whenever it will get to the CDN, the Alpine CDN server, it would go to my server that's below. And then I went IPK update, and it stopped running fetch, and it stopped here. Now, why did it stop? Because I put the payload there with the netcat listening. And then on the second server, I just ran netcat, and then I get a shell. I'm boot, I'm running ls, doing whatever I want. When I end, it gets a segfault, but I already did whatever I want, so that was it. All right. So if you have any questions, I'm going to be here. You can come and ask. Check out our Twitter. We just started a new Twitter for our research team. We have a blog. That's it. Thank you.